And so, yeah, so I'm giving this tutorial. It's based on a tutorial by Sebastian Guezel that he gave 3 years ago. And also, he wrote a lot of the manifold library in Lean. So I would want to thank him for both those things for this talk. And when doing manifolds, you start to notice that there's a couple extra difficulties that we haven't seen in other topics we've covered so far. Like it's really a more advanced topic than many of the things we've seen. And the first difficulty is that different books have different definitions of manifolds. Like if you open multiple books on differential geometry, you'll likely see that, I mean, none of them really agree on the details of what a manifold is. So here are some questions what you can ask. What's in the definition of a manifold? So like the field that you're working over, do you require that it must be the real numbers or the complex numbers? Or do you allow like more general fields? Do you allow manifolds of infinite dimension, or do you restrict yourself to finite dimensional manifolds? Do you consider manifolds with boundary manifolds, or do you only want manifolds without boundary? So your manifolds are modeled by some model space, and can that model space depend on the point in the manifold, or should it be the same model space for every point of the manifold? So these are some of the design decisions, like choices you can make in the definition of a manifold, and different sources use different choices. So I believe that Bourbaki says yes on questions 2 and 4. So they allow manifolds of infinite dimension, and the model space can depend on the point of the manifold. Yeah.
What kind of dependencies they are on the model space? Is it sort of on connected components? It's constant.
So on connected, so you can even if you allow indeed the model space to depend on the point, then on connected components it will be constant, or that they. Yeah. For example, yeah. But yeah, so Bourbaki does not allow manifolds with boundary in their definition. And in Lean, we want to start with a very general definition because, I mean, in a book, what you can do is write a whole chapter on manifolds without boundary, and then at the end of the chapter, or maybe in a later chapter, say, oh, here are manifolds with boundary, and they work basically the same. Here are some things you have to think about. But in Lean, you cannot do that, or at least if you do that, you have to like duplicate all the code that you've written for the first definition. So in Lean, we've decided to give a very general definition of manifold. So in particular, we don't assume that the field over which we take the manifold is RC, but it can be a generic or a more general field. I don't actually know any examples where whether it's actually useful to have this generalization, but so manifolds are done over the p-Alex. Okay, yeah. So so we include that in the definition. We don't assume that manifolds are finite dimensional, but of course some results are restricted to finite dimensional manifolds, and we allow manifolds with boundaries and even with corners. So the last point, we decide that we don't allow the model space to depend on the point. And as was already mentioned, that is not a restriction if we restrict ourselves to connected manifolds. And those are the most interesting one because every non-connected manifold is just a disjoint union of connected manifolds. So at least if you work in the connected components, then our definition is not actually a restriction in that sense. So what goes into the definition of a manifold? So actually, maybe it's good to also just draw something on the board. So we have this vector space E, And then, so often manifolds are modeled by a whole vector space, but if we want to allow boundaries or corners, then maybe actually our model space will just be a half space or a quarter space or something. So we have this.
Sorry, can I ask?
Yes.
When you say corner, you mean just a product of two manifold with boundary?
No, it can be the corners kind of like codimension two or higher. It, hmm?
Like an octant.
Yes, exactly. Those are also allowed. Yeah, I cannot draw that easily here, but indeed that is allowed. But so we have this vector space E, and then we have like a properly chosen subset, which could be a half space or a quarter space or an eighth space, which actually models our manifold. And then we actually have like our manifold M, and then at each point we have some local chart that corresponds to some point in H, and so that is locally homeomorphic to H. And then on the boundary of M, maybe we have a chart that models the like a point on the boundary of H. So that is sort of the idea. So we have this space of charge, this structure of charts, um, that consists of a set of partial homeomorphisms, uh, and we have sufficient partial homeomorphisms to cover M. And then we have compatibility conditions, and those compatibility conditions can also change on the manifold. So for a topological manifold, there's no required compatibility conditions between the charts, but for smooth manifolds, we need to know that if we take two charts, and we start with take the function from one chart into the manifold, and then on the intersection go back to the space. Then that composition is for smooth manifolds, or analytic for analytic manifolds, or whatever other condition you want. And so yeah, so manifolds can also depend on how smooth we want to require them. Of course, there are CK manifolds. And yeah, and then in particular, smooth manifolds are the ones with the smooth model structure. Um, and yeah, so and so all of these things are parametric on the manifold. So we can change the age, we can change like what condition we require on the compositions of two charts, and those give all different notions of manifolds. And so we have a lot of flexibility to use in a very wide range of areas, and that will be useful to have a generic way to work with manifolds. So let's look at a couple examples. So here I'm going to talk about the unit interval as a manifold. So here I is just notation for the unit interval 0, 1 in R. And that is, of course, a manifold with boundary. And so in Mathlib, we have that this fact. So we have this notion of charted space. And that has two arguments. So the first argument is this H. So what is the model space? And in the case for the interval, the model space is like the half space, or well, the one-dimensional half space, so just a ray. So this Euclidean half space is well, it works in Rn, but for R1, it's just the interval from 0 to infinity. And then we say that yeah, so we say that is the a charted space structure on I, and this is something that is in Mathlib. So, and these things are nice type classes. So I don't know if you've seen this infer instance tactic before, but that is just that is just asking Lean, oh, please fill this type class argument automatically. And normally you don't have to write anything for this. Lean, if you use something that requires this charted space argument, it will automatically be found by Lean in the same way for groups and rings and stuff. So this is saying that I is a topological manifold. And to say that it is a smooth manifold, we have this different predicate. So we have to specify what is the, so if we take the composition of two charts, then this lies in some groupoid. And to say that it's a smooth manifold, it has to lie in the groupoid of smooth maps. So this is, so this con-diff groupoid is the groupoid of smooth maps. And or at least of CK maps, and then we apply it here to infinity, so that gives the C infinity maps. And so this next example is saying, yes, I is indeed a smooth manifold with corners. And we also, specifically for the case, for the smooth maps, we have abbreviation for that, just saying that I is a smooth manifold with corners. And yes. So this it's the dimension. So let's see, this R delta. This I don't get a nice mouse over explanation what R delta is, but so R delta is this model space. So it's the model. So yeah, so in Lean it's slightly different. So we have this H, and but H is actually can be a different type than E. So actually, we have this inclusion map of H into E. So this is the inclusion map, and this R delta is the name for the inclusion map from the half ray, or well, the half space into Rn. And if you apply to one, it's the inclusion from the half ray into the real line.
So that the one there is there because you're using I, which is a one-dimensional.
Exactly. I could, yeah, indeed. Yeah, so that this is saying that things are, and I'm intentionally not showing you the definitions just yet because I want to talk a bit later about the design decisions. So in Lean, we're not assuming that the atlases of a manifold are maximal. So in fact, this charted space for the interval contains, I think, only two charts because you need two charts to deal with the two. You need at least two charts to cover the interval. But then you can say, well, given a particular given like this charge space structure on I, give me the maximal atlas of all charts compatible with the two given charts. And that is this maximal atlas definition, which from a given manifold, you get the maximal atlas on it. So we can talk about the maximal atlas. Yes. Yeah.
So if I understand correctly, the atlas that you chose from a part of the data.
Yes. Yes.
Previously in the algebraic geometry lecture, we saw that the definition of a scheme, the local isomorphism, so that the isomorphism that identifies a whole neighborhood point with the spectrum of a ring, these are just in the definition. It just says they're assumed to exist. It says the set of such isomorphisms not empty. So that was somehow a conscious decision there to not make it part of the data. And now here, it seems to be a very similar situation, and you made a conscious decision that isn't included in the data. So is this implementation related, or is it really some different mathematics? There's a different tradition in two areas.
It's so it's definitely indeed a decision you have to make, and actually.
Locally affine part that uses the existing locally affine. Yeah,
So yeah.
You have different witnesses for that when you change the scheme. Whereas here, you have different.
Yes, but it's actually like.
So you need to impose an atlas. I mean, the atlas is part of the definition. That the choice of an atlas.
Say mathematically different smooth structures, and like S7 has 28 different smooth structures.
Yeah. So Yeah, so indeed we make some non-canonical choices in the definition of a manifold, and that means that equalities between equalities between the manifold structure is not the mathematical correct equality. Like two manifolds can be diffeomorphic but not equal.
In your case, you could have added an extra open chart, like the open interval from 0 to 1, it would have been a different manifold.
They would be unequal manifolds according to Lean, but of course they're diffeomorphic. Yeah, exactly. And actually, I'll talk a bit about design decisions later, and I'll make some. I'll show you that there's some more non-canonical choices in the definition of manifold, and in this case, it's for convenience. It happens to like having some data in the manifold explicit, even though it's non-canonical as data, is actually quite convenient. So, any other questions about what I've shown so far? So another example I want to show before digging into the design decisions is the sphere. So this was formalized mostly by Heather Macbeth. And so now we don't have a general theory of closed submanifolds yet, unfortunately. But we have that the sphere is a manifold. So for example, here I'm saying let E be a finite dimensional inner product space. And this condition looks maybe a little weird, but so we're saying that E is an n+1 dimensional vector space over R. And then this fact here is just some condition, some mechanism to turn a proposition into a type class, and that means that things can use this fact without having to explicitly write why E is finite dimensional with dimension n+1. And given that we have again manifold structure on the unit sphere in E. And now the model space is this Rn, which is just a full model space. So it's modeled in this case over R to the n. And then we also have things like, for example, the map from the sphere, the inclusion map from the sphere into E is smooth. And I'm using a bit of a quite magical definition here. So this is sort of notation for the identity function, what I wrote here. And then Lean automatically inserts a coercion from the sphere into E. So I can say, but yeah, so this is notation for the inclusion map from the sphere into E. And then in particular, in the one-dimensional case, we also know that the circle is a Lie group, where the circle is just the one-dimensional sphere. So this is just some a glimpse of seeing like some of the manifolds of Lean in action in concrete cases. I don't think we have that in Mavlib yet. The group structure in S3. Okay, so now let's dig into some of the definitions of these of the things I mentioned.
So, and circle is just a synonym for.
Yeah, it's actually I can jump to it. It's the unit sphere in the complexes.
Okay.
Yep. So there is a couple. I mean, there's many moving parts in the definition of manifolds, and some of them we have to make some design decisions to make them make using like working with them nice. So I talked about these like partial homeomorphisms or partial equivalences between this model space and M. And there's many, like there's different ways you can encode that like mathematically. What is this like local homeomorphism? So this is a notion called local homeomorph in Mavlib. And so one thing we can just do is we say it's a map on a subtype. So we say, so what is local homeomorph, say, so local homeomorph HM. So we have this H, we have M, and the question, and so one definition which probably mathematically makes most sense is you choose some set here. We want it to be open, so some open set here. The domain, that's called S for source, and then it's a map from S into M, and then that map has a certain range, the targets, and that is a perfectly well-defined definition. The disadvantage with a definition like this is that if you then have this this local homeomorphism F, and you want to apply it to an element in H, you have to always prove that it's in the domain of F. So, for example, if you like compose these two charts, like you start with this point in this chart, you move it here, and then you want to move it in this other chart back to H, you have to like keep proving over and over again that it lies in this source, and that is kind of inconvenient. Of course, when proving things about these maps, we always have to like know that it makes sense. But so because of this inconvenience, we decide something else. So another option is to say, well, this f is a function on the whole space H. Oh, and of course, I should mention it's a local homomorphism, so there's also an inverse going back. And that those are inverses of each other. So another choice is f is a function on all of H, but I add an additional point maybe in M and say, well, everything outside of the source of f is sent to this extra point of M. And similar for f inverse, everything outside is sent to like a particular point added to H. And then, so that has the advantage that at least the functions are total. Like I can always apply them to any point in H or M. But actually, like it's also inconvenient because I have to then like when I want to compose f and f inverse, I have to like take care of these additional points, and that actually makes life just as annoying as before. And so what we actually do in Mavlib is something even, well, mathematically maybe even less elegant. And that is f and f inverse are just maps on all of H and all of M. And we only care about what they do on S, what f does on the set S and what f inverse does on the set T. And outside those sets, they can do arbitrary things. And I mean, this is similar to, and they're just junk values. And this is similar to like division by zero. What I think we already talked about that in lean, x divided by zero is just defined to be zero, and that is just for convenience. And yeah, same here. We just for convenience say, well, they are points. They are defined as something. We just don't know what. And it works perfectly fine, but mathematically it's a bit unsatisfying because, of course, the equality of two local homomorphisms is now not the right notion anymore because it depends on the values outside the source and the domain. So how this looks in Mavlib is, I don't know if you've already seen this equiv. So equiv is just a bijection with an explicitly chosen inverse. So an equivalence between two types is just functions back and forth, and then they are inverses, two-sided inverses of each other. And so then we can take a notion of a local equiv or a partial equivalence. That is a bit more complicated, but it's the same idea, but they are restricted to subsets. But here you see, so the functions tofun and infun, they are really functions on the whole, on all of the types. but then there's a designated source and target of the domain and the codomain, and we only assume that the two functions back and forth are well behaved on those source and target. So we assume that the forward function maps the source to the target, and the backwards function maps the target to the source. And on the source and the target, the two functions are inverses. And we don't have any assumptions about their behavior outside the source and the target. So that is the definition of a local equivalence. Does that make sense? And then we have a local homeomorphism. So that extends a local equivalence. So every local homeomorphism has all the properties and data of a local equivalence. But then there's a couple more conditions. Namely, we assume that both the source and the target are open, and that the maps are continuous, at least when restricted on the source and the target. Yeah, so this continuous on predicate says that the function is continuous when restricted to that subset of your domain. So that is sort of the first design decision that might be a bit controversial. Another design decision is about tangent vectors. So there's many different choices you can make for the definition of tangent vector. You can say, we look at all the curves through that point, and then we look at all the germs of the of curves, and then like we take equivalence classes of those. Actually, this is a little inconvenient because, for example, on the boundary, it's kind of annoying to define that, or at least we have to define that separately for points on the boundary. We can define it as a derivation, but that is also kind of annoying to work with. Another thing that makes sense is, well, I don't know what a tangent vector is, but I know at least what a tangent vector is in the charts. So that might be a physicist's way of saying it, and mathematically you can make that precise by taking equivalence classes of like charge around the point, and then like a vector in the vector space, and then like an equivalence class if they give the same answer up to this the coordinate change induced by the two charts. And this is also quite annoying to work with because you have to work with these equivalence classes. And there's a lot of things to check. And so in Mathlib, we take a bit of a shortcut. And that is that around each point in a manifold, we have a favorite chart. We have a designated chart that is sort of the canonical chart around that point. And then we define the tangent space. So at each point, we have a favorite chart, and we define the tangent space at this point to just be the space E viewed through like the local homeomorphism given by the designated chart around that point. And this might make you a bit uncomfortable because, again, it's like this non-canonical choice, but it works actually quite nicely, and you don't have to work with these equivalence relations. So let's see, and yeah, and so in the definition of manifold, there is actually this designated chart. Yeah, what's your?
Definition 4, I'm wondering, does it become harder to show that the derivative is continuous in the appropriate time?
I mean, so not necessarily. So there are of course lemmas. So of course we still need lemmas that if you look, for example, to show that a certain map is smooth at a point or something, you have to. So it's easy to say what that means if you look in your favorite chart in the designated chart. But of course, we also need the property. What happens if you look at a chart that is not that contains that point, but is not your favorite chart? and then we do need, and we have a lemma saying, oh, it's still the thing you expect there. So it doesn't like remove like all the proof obligations or something. Like we still need to prove that, oh, in other charts it's still the sensible thing, but at least the definition is quite a bit easier.
But there's no requirement that say all the points. So if you fix a chart, you don't require that all the points who have this particular chart as the fatal chart that they fall over subset or something.
No. So every point could have a completely different chart as their designated chart. But of course, like in a smooth manifold, all the charts are compatible in the sense that the coordinate changes are smooth. So it doesn't actually matter which chart you choose. But this is again another like non-canonical choice in the definition of manifold. And so so equality of manifolds is not the right thing. You have to just talk about diffeomorphism of manifolds.
If you change the point, E is still the same?
Yes, E is constant throughout the.
How can you define the tangent bundle?
Well, I'll jump to the definition in a few seconds. But let's first look at what actually the definition of this charted space is. So that is a topological manifold. So a charted space comes with an atlas, which is just a set of these partial homomorphisms or local homomorphisms between M and H. So these are the charts. And then for each point, so this is the chart at, for each point M, in M we have our chart at that point, which is a local homomorphism, and then just two predicates about these chart ats. So the first property is that the chart at X must actually contain X in its source. And the second is that the chart at X is actually in the atlas of the charts of our manifold. So that's what a charted space or topological manifold is. So yeah, so these designated charts are like baked right in the definition. And then the definition of tangent space is really not very interesting, at least, well, I mean, it's not very complicated. So we have this tangent space, and it takes this manifold, which is a smooth manifold with corners, and a point X in M. And the definition of tangent space, oh, it's just E. And this definition is obviously the wrong definition. It is, of course, the tangent space is isomorphic to E. But then, like later in this file, we're going to add a bunch of structure on this tangent space to make sure that it's E but equipped with a different structure, and that makes it still the right definition. And one thing that I find funny is
like the disjoint union of all the tangent spaces, and then you put an extra topology later on.
Yeah, so the tangent bundle is indeed the disjoint union of a whole bunch of copies of E, and then we're then gluing them together, like, or putting the right topological structure on it. And yeah. So one thing that is funny is, so we have this unused arguments linter as a style checker for lean, and of course lean. So we have to say here, oh yeah, this definition is allowed to contain unused arguments because it depends on all this data that is unused, and the definition is just E. But of course, all the structure on the tangent space uses a lot more data. Yeah, and so and then the tangent bundle is just the total space. So view the tangent space as a bundle over M, which actually independent type theory is just a dependent type. So it's just for every point in M, we take a type, which in this case is just E, and then we just take the total space of that.
This is more a lean question. Can you go back to the previous?
Yes.
The no linted one. Can you remove the underscore under X before X?
Yes. And then lean will complain. We have actually two ways to lean tells in two different ways that things are unused, and so we also have a linter that checks if you name something and then never use it. In the standard one, exactly, and they have slightly different scopes, and so both of them are useful. And so to disable it, you can start your name with an underscore. But yeah, that's Okay.
So right now, your definition of tangent polynomial was dependent type, but it was like constant at e, so just e times n, basically.
It is e times n, yes. Or it's, yeah, exactly.
But as a without the structure, just as a type.
Yeah, yeah, exactly. But it has a completely different structure than e times m, unless if it's trivialized. Yeah. Okay, and then and then there's a comment on smooth functions. So if I actually have a manifold with boundary, then what does it mean for a function to be smooth at a point on the boundary? Because of course, then like this is mapped to some point on the boundary or in the corner of your model space, and it's kind of unclear what it means to be like smooth at a point. And actually, in many textbooks that cover manifolds with boundaries, you actually have to extend your function a little bit beyond the boundary, and then you're smooth. Um, Smooth at the like then your point on the boundaries in the interior, and we can talk about smoothness. But that extension is like kind of inconvenient to work with. So in Mathlib, even for maps between vector spaces, we already have this very nice notion of being smooth at a point within a particular set that might not be open, but might just be like it might be on the boundary of that set. And this was also done by Sebastian with like specifically manifolds with boundaries in mind. And so we have this predicate like a function is continuously differentiable. So this is at this point we're just talking about functions between vector spaces. Is continuously differentiable at a point within a given set, and that is like uh, baked into the definition of smoothness right from the start. And that allows us to very conveniently talk about these manifolds even with the points on the boundary. So this definition is kind of complicated, but it sort of says that yeah, you have a formal multilinear series to be like yeah, to be n times differentiable up to n.
Sorry,
Yeah.
does it
Yeah.
mathematically imply that the function actually extends to a smooth function, or is it neutral?
I'm not actually sure. Think it. I'm not sure.
It seems
It
weird
might be
to
a.
detect extensibility just by testing it on one side.
Yeah, it only so yeah it only depends on the points inside that set. So yeah, I'm not sure. Um, Yeah, so one thing that you have to watch out for when doing this is that if you if the set you're considering is too small, your derivatives might not be unique anymore. So for example, if h would just be a line in R2, then we know like what the derivatives like if I have a map on A that has domain H, like I know the derivative of a function is well defined in one direction, namely in the direction of H, but it's just not defined at all in the direction perpendicular to H. And so so derivatives might not be unique, like we in this case like the derivative can have any behavior in the direction perpendicular to H as long as the behavior in the direction of H is correct. And so we also have this like unique diff on predicate, which just says that functions have like unique derivatives inside your model space or your subset of your vector space. And so the model space for a manifold is assumed to have unique derivatives, so that we can define what it means for a function on a manifold to like to have a particular derivative. Yeah, and so and then from that, like from this setup, we can then define like in Mathlib we have the notion conv diff, which is for maps between vector spaces. or norm spaces to be differentiable. And then we have Kant MDiff, where the M, of course, stands for manifold, which is a map between manifolds being differentiable. And so this is a bit ugly to read here, but so this is, for example, the characterization. So F is a map between two manifolds, M and M prime. And to say that the map F is smooth, or like n times differentiable at a point, is equivalent to saying, well, it's continuous at that point. And then in these charts, like what we see here is roughly the function viewed in the chart. So and then that must be continuously differentiable inside like H. Yeah, so there's a bit much to unpack, but this is roughly what I mean. This is making precise what is done in textbooks, like for continuously differentiable. So one thing, I'm close to the end of my time, but that's fine. So one thing that is a bit annoying when working with the manifold library is that things are a bit verbose to state in Lean. So all these lines are just saying let M be a smooth manifold. Or to be more precise, let M be a smooth manifold like modeled by the space H, which is sort of you can view as a subset of the vector space or the Banach space E. So E is a norm space, H is just a topological space. Then we have this model with corners, which is basically just this map from this inclusion map from H to E. And then M must be a topological space with a charted space structure that we saw, and then it is a smooth manifold with corners, which is just saying the charted space are compatible. So like the coordinate change between two charts is smooth. And if we have two manifolds, then we can do some things. For example, we can write down the derivative of a map. So if F is a map from M to N, then at a point X, it induces like the derivative on the tangent spaces. So it's a continuous linear map. So this is the notation for continuous linear maps from the tangent space at X to the tangent space at F of X. And it's this F deriv is the name for it. And of course, if F is not smooth, then this MF deriv is just a junk value. So it only makes sense for smooth maps. But for example, if you assume that G and F are composable functions that are differentiable, then for example, here's the chain rule that which says that the derivative of G composed with F at a point X is the composition of the two linear maps. And of course, a map also induces a map on the total spaces of the tangent space or on the tangent bundle. And here's, for example, an example using Lie groups, which we have in Mavlib. So if F and G are both n times differentiable and their codomain is a Lie group, then the sum of the two functions is also smooth. And that has a very nice short proof using the dot notation. So this is Kant mdiff dot add, and so therefore you can write hf dot add hg to do it. And then we also have vector bundles, but I am basically over time, so shall I just stop here, go quickly through it? Okay, yeah, I'll take another 5 minutes to like quickly talk about it. So we have a couple different notions here. So we have smooth vector bundles and then like the weaker vector bundles and fiber bundles. But it starts with the definition of a trivialization of a or local trivialization of a vector bundle. So here's the definition. So suppose we have just a map from like Z, which is you can view as the total space of a fiber bundle, say, to the base manifold B. And then a trivialization of that is just local homomorphism from Z to B cross the fiber. And then some properties to say that it's actually trivialization. So it's a trivialization on, maybe I should just draw a picture. So we have this base manifold B, and then we have this total space Z. And then, so a trivialization takes some base set where it is a trivialization, and then it is sort of a local homomorphism of like all the points that are above this base set of B to so it's a homomorphism between this shaded area and here is B, so B cross F is this space, which is yeah, good point. Exactly. So this is A. But it's implemented in Mavlib as a local homeomorphism to B cross F, indeed. But indeed, the range is A cross F. And so then these properties are saying saying that the local homomorphism actually acts as this picture. So the base set must be open. The source of the map must be like the pre-image of the projection map of A, of the source. And the target must be indeed A cross the universal set of F. So that is this base set cross unif. Oh, and it must commute with the projection map. So
you answered one question before when you talked about
okay, yeah. So that is a trivialization, and then we have fiber bundles, which are basically in a set of trivializations as before. And we are doing the same trick here as we do in manifolds. Namely, we also have a canonical preferred trivialization at each point. And then the same two conditions that the point actually lies in the base set of the trivialization, and that this canonical trivialization lies in the atlas. And then we have vector bundles. So that is has the additional condition that this fiber is a vector space, and like that this map is sort of fiber-wise linear. So if you take a fiber of over a single point, and then a fiber here, then the map induced on those fibers is linear. And then actually a smooth vector bundle is saying that like the coordinate changes between two of these trivializations is actually a smooth map. So we have all these definitions, and then here I'll show you a little bit what you can do with that. So here again we have this verbosity issue where you have to write quite a bit. So this is all saying like F1. Oh, sorry. E1 is a smooth vector bundle over the manifold B with fiber F1. And then here is another smooth vector bundle. And then we can, for example, do a couple operations on vector bundles already. So we have the product of two bundles, and that is again a smooth vector bundle over with the product fiber over the same manifold. We can also take the continuous linear maps between two bundles. So this bundle that contains linear maps is the linear maps between two bundles over the same manifold. And that has as fiber the continuous linear maps between the fibers. And we can pull back vector bundles. So, so this is notation for a map that is already smooth. And then we can pull back that from that map. Sorry, using that map, we can pull back the the smooth vector bundle E1 to a vector bundle over M, and that is again a smooth vector bundle. And then finally, I want to flash a definition or something that a teaser for Oliver's talk tomorrow, which is that we proved that we can turn a sphere inside out in R3, so the two sphere, and we did prove this from Gromov's principle, and this is the statement using some nice notation that I declare here, but I will talk more about this tomorrow. So that's it for now.